The final equation that we need to close our system of equations and allow us to solve for the entirety of fluid dynamics is that we need an equation of state. Now, in most cases in astrophysics, we can assume an equation of state that is based off of the ideal gas. So let me share my screen and I'll take us through a few steps of this. So if we can assume that we have an ideal gas, then we know that for an ideal gas, the pressure is equal to nkt, where n is the number density, or in most of our equations for our fluids, we've been considering this in terms of rho, the mass density. And so we can rewrite this as K over mu, which is the mean molecular weight, times the mass of a proton, times rho, times temperature. But now we have a new variable. T. And that doesn't sound good. And furthermore, can we even consider gas in astrophysics to be ideal? So I'll take the second one of those first. And the answer to that is yes. For the most part in astrophysics, we can consider our gas to be ideal. We know that gases only show ideal behavior when they're warm and relatively dilute. But if they start to become very, very cold or they compress a lot, then the potential energy of those interparticle interactions kicks in, and that becomes important when compared with the kinetic energy of the random motion. But that's not usually the case in astrophysics. When we talk about dense gas, it's nothing like the density that we get in terrestrial situations. A dense gas may be something on the order of 1 million particles per cubic centimeter. But even the air we're breathing has 10 to the 19 molecules per cubic centimeter. So that's not in any way a dense gas when you're talking about a density of 1 million particles per cubic centimeter. So most of the universe is extremely dilute. Most of it is relatively warm by comparison, and we can apply the ideal gas law. But the ideal gas law, as we've just said, introduces a problem because we've just replaced our pressure does relate to our density, but now we've got a new variable, temperature, and we would need yet another equation to close that off. So instead, what we want to consider is we want to consider situations where the equation of state is barotropic. And so that means that we want to consider barotropic situations are those where the pressure relates only to the density. So we want pressure to be a function of density. And there are two ways that that can come about. One is that we can have an isothermal situation, in which case the pressure is proportional to the density. So based off of my ideal gas law, I have that the pressure would be proportional to the density, the temperature wouldn't change. And that works in situations where we consider thermal equilibrium. When the heating and balances out the cooling, there's no change in temperature, and we can work straightway with an ideal gas law at a constant temperature. That's not always the case either. We can't always work with that. And so what we want to consider in the second possibility is to consider adiabatic. So we can consider adiabatic scenarios. In that case, the pressure will be proportional to the density to some factor gamma. And by adiabatic, what we mean is that the ideal gas undergoes reversible changes. Now, in general, that's also true. We can compress the gas and then let it expand again. There are some situations which are not adiabatic, like shocks, and we'll get on to shocks in the last week of the class. But for right now, let's consider just a simple case where we have an adiabatic gas. And there we can work from the first law of thermodynamics to show that we can write out an equation for our barotropic gas. So rather than work all the way through that proof, let's just work through the idea that for an adiabatic gas, the pressure is equal to some constant times rho to the gamma. And gamma, in this case, is the ratio of the specific heats. It's the ratio of the specific heat at constant pressure to the specific heat at constant volume. And we know that if the gas is monatomic, I should say. It's monatomic, that the specific heat at constant volume is 3/2 over K over MP. And we know that Cp minus Cv is equal to K over MP. And so it follows that gamma would be 5/3. And that's for a monatomic gas. In the situation of a diatomic, it would follow through that gamma would be 7/5. Now, for the most part, in this class, we're going to work with monatomic, and we're going to consider this case of having the pressure equal to K, which is a constant of some sort, times rho to the gamma. And we're going to usually let gamma equal 5/3 for our case. Now, if the fluid element behaves adiabatically, then K is a constant. And in other cases, K can be a monatomic function of entropy, but we're not going to consider those to be too worrying in the immediate future. So we have a very simple equation of state. And from there, we can summarize our fluid equations. And the fluid equations go as follows. Once again, we have the change in density with respect to time. Plus the divergence of rho u is equal to 0, and that's the continuity equation. We have that rho times partial derivative with respect to time of the velocity field plus rho u dot grad u is equal to minus grad p plus rho grad psi. And that's Euler's equation. We have Poisson's equation, which is grad squared psi equals 4 pi g rho. And finally, we have the equation of state, which relates the pressure is equal to a constant times the density to the gamma power, and that's an isobaric equation of state. And with those, we now have equations, 4 equations and 4 unknowns, where those unknowns are the density, the pressure, the gravitational potential, and the velocity field. And we can put those together to solve for the entirety of a fluid dynamical situation. And as we move on into our next week, we'll start to perturb the situation to develop instabilities, to propagate sound waves, and to carry information through the medium via these fluid equations. And we'll stop there.